Hello and welcome again in my channel. Today I bring to you a new video related to the benefits of multi-pump arrangement, which is related to the configuration of pumps, either parallel or series configuration. So let's begin. So here we can see the series configuration as well as parallel configuration based on consideration in system design. Either it is in parallel or it's in series, other than selecting one pump only to operate, which is lead to more capital cost in the system, large capital costs from redundant backups, and inefficient operation under diverse operation conditions, and challenging system requirements for successfully operation. That means if you use only one pump, there will be no efficiency in the system, and it will be against the operation requirement. Maybe it will be idle sometimes, and it will be breakdown, so it will fail in the system, other than using the parallel or series as per your requirement for higher head or higher flow. So as we see here, this is an example of composite pump curve comparing parallel operation and series operation, the source from Applied Flow Technology website. So this is the configuration of series, and this is the configuration of parallel. We can see how the difference in series, it is going to the higher pump head, pumping system head, but in the parallel it will go to the higher volumetric flow rate in the system. Why consider a multi-pump configuration? The reason why we are considering this mainly to capitalize on cost savings. There are many benefits to configuring multiple pumps instead of relying on a single pump for a system. By approaching pump sizing with these alternatives in mind, there are more opportunities to capitalize on cost savings and improve pump operations, as well as create additional flexibility in the operation of the system. The primary benefit of using a multi-pump configuration is spreading the system's workload across many smaller pumps instead of relying on a single large pump. In circumstances of large flow rate and large head requirements, a custom single pump may be more expensive than a collection of smaller pumps. These smaller pumps are more likely to be off-the-shelf components, more reliable, more cost-effective to maintain, and easier to install. Similarly, the smaller motor would be needed, against improving capital cost and hopefully creating long-term energy savings over the life of the system. Often, software can simply analyze on the recurring and capital costs of different pumps alternatives, informing an engineer's economic decisions during the design process. During operation, multiple pumps create flexibility in a system by providing several potential operating points. A collection of pumps allows for a single pump to meet low flow demands, while several pumps together could meet higher flow demands. Designing the multiple pumps running continuously also allows for improved redundancy measures. In single pump system, a fully redundant pump is required to maintain flow during maintenance or emergencies. Multiple pumps ensure the majority of a flow requirement is met. If one pump has issues that requires maintenance, this is also more cost effective than a fully redundant pump, especially in the case of massive high head or high flow rate pumps. In many cases, the analysis of design alternatives is expedited by software to compare different operation conditions and test pump operation in imperfect scenarios. Here we can see configuration pumps in series and in parallel, and we can see a comparison of parallel and series operating for steep and flat system curves, showing the different of operating point for each system when we are using steep or flat curves systems. Series vs parallel pumping. Pumps can be oriented in series, parallel, or a combination of configurations. Pumps in series add each individual pump's head rise as the same flow rate passes through each pump. Pumps in parallel operate at the same head rise with potentially variable contribution to flow. Each pump in parallel generally sees the same inlet and outlet conditions, thus requiring the same head rise to be effective, as will become evident through some examples. Combining differently sized parallel pumps can cause operating issues due to this head rise requirement. As we've seen before, in the image number 1 demonstrates how operating pumps in each configuration contributes to a composite pump curve. Pump and system curves prove useful when comparing configuration and determining potential operating condition. System aspects of pump system interaction. In nearly all cases, flow will increase by running an additional pump. The amount that flow rate increases is determined by the pressure demands of the system and the composite pump curve. The system's demand, characterized by the system curve, has two main components, which are the first component, static head. Static head describes head the pump must overcome regardless of flow rate. Static head can include changes in elevation or difference in pressure from system inlet to system outlet. The static head requirement is where the system curve has zero flow. The second component, friction head, increases head demand with increasing flow rate. Friction head also captures losses due to components, indicating the slope of the system curve can shift with changing operating conditions such as valve position. So the first component, static head, second component is friction head. Here we have the friction head, which is must overcome regardless the flow rate, and the friction head increases head demand with increasing flow rate. The effectiveness of an additional pump largely depends on the system. For cases with low friction head and thus a flat system curve, operating pumps in parallel should increase flow rate more than operating the same pumps in series, as we've seen in the curve before in this video. In cases of high friction head, such as narrow rough pipes with many components, operating pumps in series can provide more head to meet system demands at higher flow rate. The resulting flow rate from each configuration in each system can be found in the previous image, which we've seen before in this video, and we elaborated it for steep and flat system. Notice in all cases, flow rate will increase slightly compared to the single pump curve, but with a drastically different return on flow rate for running an additional pump. Extrapolating the pump system concept reveals the various operating conditions a system can achieve by staging several pumps. There are energy saving by selectively running pumps at various system demands. This slide for dissimilar pumps in parallel indicate no contribution by small pump at the system's operating point. So in the small pump and in the large pump, there is no contribution by small pump at the system operating point. Dissimilar pump configuration, which we seen a while ago in the curve, there are also benefits from using dissimilar pumps in parallel or series, while the concept of staging applies largely to uniform pumping stations where each parallel pump is identical. Different pumps can similarly provide additional operating points for a variable demand system. For example, operating a large pump parallel to a small pump ensures flexibility as demand shifts. By shifting which pump operates, the small pump can meet small demand while the large pump can meet large demand, as we see in the curve. This creates energy saving while also providing operational benefits, as each pump can operate closer to its best efficiency point. In the parallel pumping system configuration, we have two options in this configuration. Either both pumps are the same in characteristics, that means pump A is the same like pump P in the flow and head. In the second configuration, we have pump A is different to pump B in their characteristics. That means the head and the flow are totally different for both of them. So we can see the difference in the system curve for the both cases. In the first case, if the pump A is equal to pump B, we have the system curve, the pump curve, operation curve for the both of the pumps are the same. System curve here, we have the same flow and the same head for both of the pumps. When we are using them together, we have the total head is the same for both of them in the system for the both of the pump running together. We have HA equal to HB, while the flow is equal is the sum of the flow for the both of the pumps. That means QA plus QB. In the second case, we have everything will be the same. The total head also the total flow will be the sum of the two pumps, but every pump has different configuration curve, that means different flow and different head. But in the total, we have totally in the operation point here, we have the head is equal for both configuration together. It is giving one head, but it is giving the total flow for the pumps, QA plus QB. So as we've seen in the curves, while having the similar pumps in parallel can improve operation when each is run independently, improvements by running both at the same time largely depend on each pump's respective pump curve and the system curve. Imagine a case where a low flow, low head pump is competing with a large flow or high flow, high head pump. In parallel, these vastly different pump curves will be summed as the same head rise as before, as we see in the image demonstration. The limited contribution a small pump can make when operating dissimilar pumps in parallel and system requirements exceed the small pump deadhead. In several cases, the large pump's lowest head may exceed the deadhead of the smaller pump, indicating that the small pump cannot contribute to increasing flow while the large pump is running. This mismatch can also lead to backflow issues through the small pump if not addressed with a check valve or similar isolation valve. Multiple dissimilar pumps can also be used in series to solve operational problems during pipeline distribution. For example, imagine a long pipeline with severe changes in elevation. Since pressure requirement increase with pipe length, a single pump would need to add massive amount of pressure right at the pump discharge. With this high pressure as basis, there can similarly be high pressure when the line drops in elevation. The fluid may experience cavitation from the drop in pressure at high elevations further down the line. Rather than relying on a single pump, booster pumps can help avoid exceeding the pipe pressure limitations or ensure there is sufficient pressure to avoid cavitation in the middle of the line. Similarly, booster pumps can help an undersized pump meet system requirements in other contexts. Now, how to consider pump configurations? While it is conceptually easy to combine composite pump curves, it can often become difficult to manage configuration alternatives, pumps options, system conditions, etc. As with many engineering issues, considering software is a viable method to quickly and adequately size pumps. In many cases, software can generate the composite pump curve and the system curve from user input, reassigning the operating point automatically from system changes. With pump operating points determined automatically, it is also convenient to check the best efficiency point proximity at each operating condition. Software can provide insight into design flows before implementation, addressing issues before they occur.
Let's see how to make pump configuration. There is a website I can show you how to make the system curve as well as the pump curves for two pumps either on series or in parallel. Let's see together. So we can go to this website. The website is checalc.com. This actually a very simple website showing you how to configure either in series or in parallel. So we can enter our system flow rates and head for our pumping system, and we can simply get for this system we can get our configuration in series or in either it is in series or in parallel for the system. Here we have two pumps are equal. So for single pump we have in series we have this the pump curve, and this is the system curve, and here is the operation point is 5.8 the flow, and the head is for the single pump is 14.6, while it is for the both of the pumps double pumps in series it is 26.3, and for single is 13.1. So this is the head, and the flow is actually it is 9.1 exactly. So we can get also the result here, the final result at the operation point. The flow rate is 9.2 and the head is 26.3. If we have system in parallel, so we can change it from here. So it is automatically it will draw for you the system in parallel, and it will show you we can see the final result here, the flow rate, the operation point, flow rate, and the head. Flow rate is 5.93 cubic meter per hour, and the head is 15.15 meter. Very easy and very simple website showing you how to do you can go through this website and you can see, you can change the parameters here, and you can see the difference in many systems.
So as a conclusion, pumps in series or pumps in parallel. In the first configuration, pumps in series, each of the pumps is adding energy into the pumping fluid. So the resultant head, H1 plus H1 equal to 2H1, or H2 plus H2 equal to 2H2, is the sum of the head developed by individual pumps. Factors to be considered when we connect pumps in series. Series operation is usually but not always opted for higher head requirements. That means when NPSHR of the main pump is very high and a booster pump to be provided with high NPSHR available is required. Booster and main pump are operated in series. When parallel pump operation is not possible because of inherent pump and system characteristics limitations. The following points are to be kept in mind while considering the series operation. First, a detailed system resistance curve is available with required operation condition. Second, the pump characteristics are available, QH, etc. And finally, the pump operating conditions are checked by only superimposing the pump Q and VSH characteristics curve on system resistance curve. Second, pumps in parallel. Pumps are operated in parallel when two or more pumps are connected to a common discharge line and share the same suction and discharge. The parallel operation is usually opted to cope up with higher flow demands, which crop up, as said earlier, because of debottlenecking or revamp activities in the plant or refinery. However, parallel operation is not the only choice to achieve higher flow. Parallel operation is possible in following cases: pumps with identical QH characteristic curves, pumps with dissimilar but overlapping characteristic curves, same shut-off heads, different shut-off heads, steep as well as flat QH characteristic curves, pumps with so-called unstable drooping characteristic curves, centrifugal plus reciprocating pumps, but avoid such operation. So, pumps in series. Two pumps in parallel will deliver less than twice the head of a single pump in the system because system and pump characteristics are not linear and cannot be added directly. In other words, a single pump will operate at a lower head than if it were working in series, parallel with another pumps. This means the driver rating is usually higher, as lower head operation means higher flow and higher power requirement. As series operation means higher head operation, downstream piping and equipment like heat exchanger and valve shall be reviewed for overpressure protection and other changes in operation conditions. consult the pump vendor and get the scheme approved by pump vendor. While in the pump in parallel, the following points to be kept in mind while considering the parallel operation. First, a detailed system resistance curve is available with required operation condition. Second, the pump characteristics are available, including NPSHR. The pump operating conditions are checked by only by superimposing the pump Q and VSH characteristic curve on system resistance curve. Two pumps in parallel will deliver less than twice the flow rate of single pump in the system because system and pump characteristics are not linear or straight lines and cannot be added directly. In other words, a single pump will operate at a higher flow rate than if it were working in parallel with another pumps. This means the driver rating is usually higher. Consult the pump vendor and get the scheme approved by pump vendor. Next, we have guidelines for designing parallel pump applications. In conclusion, listed below are guidelines for designing parallel pump installations. Try to install parallel pumps with identical head flow characteristics, although pumps with dissimilar QH characteristics can be operated in parallel. Ensure that associated pump piping is symmetrical so that flows are better balanced. Parallel pumps should have dictated flow meters installed on each pump. As a general rule of thumb, shutdowns can be set at 40% of best efficiency point flow or as recommended by the vendor. Set low flow alarm at 40 to 50 of best efficiency point, 50%. Designate one pump as the lead pump and one as the lagging pump, so that if flow are essentially equal and total flow drops for some reason, the lagging pump will be shut down and the lead pump will continue running. Use of power meters or current meters to roughly indicate flow should be avoided. The relationship between power and flow varies based on pump hydraulic design and may not provide an accurate indicate of variable frequency drive VFD installations. Always operate all the pumps running in parallel at the same speed to ensure that they are generating approximately the same head. A PLC programmable logic controller can be used to switch pumps off or on based on the current process demand, or to alert operators when pumps should be started or shut down based on the process requirements. There is always a chance of uneven pump loading in case of parallel operation, which means one of or some of the pumps take most of the flow, leaving one or other pump starving. This starving, which means operating at very low flow or below minimum continuous flow, stable flow, is very detrimental to pump, as it can lead to heating up of the casing, vibrating leading to failure of bearing or mechanical seal. This uneven flow characteristics can be because of non-symmetrical piping or system operated at flow lower than normal flow. At this point, it was the end of our today video. Thank you for watching this video. Please like and share and subscribe.